So, welcome everybody on this QuMat colloquium. I'm very happy that Polman, Professor Albert Polman, was able to come. He is well known here at Utrecht. He is a long Utrecht history studying here, and then you did your PhD also in Utrecht, understand? And then having the teaching in nanophotonics when he was already group leader and director in AMOLF. So this has been by many students very much appreciated at the time. And Albert is known for his combination of very fundamental research in, let's say, nanophotonics, nanoelectronics, and then also direct towards applications. So he did a lot of work on optical metamaterials and plasmonic interfaces, but also applied it to for light management in thin film solar cells to increase the light absorption. Is to have efficiency for thin film cell. So he's well known for that, and I think his talk today will again express deep insights and but also close to quite interesting applications. So he will talk today, his title is Nanoscale 3D plasmon holography and electron wavepackets.
Thank you for the introduction. Thank you for being here. Yeah, this is a very cryptical title, I guess, for many of you. Maybe some of you don't know what plasmon is or how it links to holography. And I think certainly the aspect of electron wavepacket shaping is maybe an aspect. Of course, the goal of the talk is that I'll explain that all to you. So I'm in AMOLF, in the National Lab, in the National Science Foundation, NPO, in Amsterdam, where we make research groups and all these various aspects of the nanophotonics. Let me first show a slide that links to what Daniel said about applications, and it's also the only one in this talk that's about that. But you always have to ask yourself first, why do we do what we do? So we are interested in nanophotonics, and that's what the talk is about. Why are we? And for me, I'm in a department that's called sustainable energy materials. So three aspects, and we all work on my research group. One is to make ultra-efficient photovoltaics. So this is a cartoon of a cross-section of a solar cell where a nanostructure is embedded in the back contact that scatters the light in such a way that it's more efficient to trap the solar cell. We also use very similar structures to make devices that we call optical metasurfaces for optical computing. You can imagine there's a surface that is structured in a certain way, the light field comes on it, on the other side comes out a mathematical operation, the light field. If you take the derivative, for example, that's useful for edge detection. It's again a nanophotonics concept because light is scattered with nanoscale features, control that scattering. And more recently, we're interested in sustainable chemistry. That's been my life. I'm not all a chemist, so I can only do this by working together with specialists. But the lighter part I like. And the idea is that many chemical processes that are normally just like just fossil fuels and you heat up a big vessel and do chemistry in there. Instead, you come in with very powerful laser beams or LEDs and drive the chemistry about. That's also where nanophotonics comes in because you can create hot spots if you know how to concentrate light at very small scales where you then selectively drive chemical layers. So these are all cartoons, but just to show you actually do this, I have just two examples. One is in photovoltaics. We just reported the world's best silicon-based solar cell has an efficiency of 36%. Because it's stacked multiple layers on top of each other with a nanophoton metal surface that passes the light travel. The other is the sustainable chemistry by light. That's not a result here to show, but it's a cartoon that was made in Vanmaekelbergh group, showing again this battle where normally chemical reactions take place, but now we drive this with light. And in there are small metal nanoparticles that if you excite with light, the light excites plasmons. Plasmon is nothing else than an oscillation of the free electrons in the metal, and you know the many, every atom in a gold nanoparticle with about one free electron. So that high C, dense C starts oscillating, and it's partly damped and it creates heat. So that's the sustainable chemistry driven by light. So in both of these, you see there's already ideas about systems and even devices, and also in the analog optical computing, this area that's rapidly coming out. That's practical as well. So I'm showing this because all these cartoons show nanoscale features of metal, dielectric. So we need to understand how light interacts with these structures. And when I got interested in nanophotonics, when the nanoscientists came up and we had some background in optics, I thought, okay, I want to get active in nanophotonics. Hardly didn't exist at that time. So the first thing I was enabled to do is here in Utrecht, start a course on nanophotonics. So it's a way for me to learn what it means. And then in doing the research, we realized, yeah, we need tools. We need tools that can measure nanoscale optical fields. And we know with optical microscopes, which are limited by the diffraction limit, scanning, electron microscope, scanning, near-field microscopes, super interesting. But that already gives you a smaller length scale with some advantages and disadvantages. And then I thought, okay, maybe I should get into another way of measuring optical light fields, and that's with electron beams. So the electron beam is the center part of this talk, and how it links with photonics. So the way this works is we have an electron microscope. It's the standard SEM. You have many of them also here. Here's the electron column, comes an electron in. And in the inside here, above the sample, is a parabolic mirror where electron beam comes in and excites the sample. And of course, I will explain what that excitation is. But the electron comes in and light comes out. That's the idea. So you raster scan the electron beam over the surface. And in every position where you place the electron beam, you take spectrum. Since you can place the electron beam with, say, 5 nanometer spatial resolution, you make optical maps with a very small resolution, way better than optical diffraction. So we raster scan and take a spectrum at every pixel. We make maps. We can also do angular collection. So then every angle at which the light is emitted is projected onto a camera, where each pixel has a unique relationship to the angle at which the light is emitted. That's how you make dispersion diagrams. The angle tells you the wave vector. So we can map the dispersion diagrams of photonic crystals. So such instruments really didn't exist, and so we invented it. We built it in our lab, and then we also found out afterwards there's a market for it. There were academic groups and industrial groups. So we founded a company based in Delft. Delft that actually sells these instruments. This is the box. This is the spectrometer that hangs here off the electron microscope that collects the light as it's collected inside. So the phenomenon that we're studying here is cathodoluminescence. That's how historically it's meant, which is a cathode ray that convenes luminescence. And that was used by geologists already in the 1970s. So if you have a piece of mineral, you want to know what it is, you stick it in an SEM, hit the electron, and the mineral starts to fluoresce. The fluorescent spectrum is a marker of calcite or so these are maps. I took these from Wikipedia of different minerals where the electron beam goes over, and you make a color plot of the luminescence that comes out. And the radiation that comes out is incoherent. So the electron beam comes in, it excites electron hole pairs that move around and recombine, or excites color centers into some higher state that relaxes down, and in the end, the photon comes out. So there's no phase relation between when the photon comes out and the excitation in many steps in between. Hundreds of femtoseconds or sometimes microseconds skips. The radiation angle distribution is the Lambertian. That's a cosine dependence here because this is an isotropic emission inside. It gives a characteristic Lambertian emission outside. The concept I'll talk about today is the coherent part, and that's much more interesting from the nanophotonics point of view, because now it's purely electrodynamics. Electron comes in, here's the substrate, so the electron generates a point and an image charge. So now you have a sudden dipole moment. As the electron comes to the surface, still it disappears. As this dipole moment is there, like any dipole that's sticking up the surface, it radiates. Upward dipole moment radiates to the side. So typically, if an electron beam comes through a dielectric interface, it will create radiation with angular lobes characteristic for a dipole. This effect is called transition radiation. Any electron that makes a transition from one dielectric to the other creates this kind of coherent radiation. Because it's coherent, because there's dipole oscillation, there's a fixed phase relation with the electron coming in. Light. So these are the two characteristic angular distribution. Let's look in more detail what happens if an electron then passes by a nanostructure. So now we're moving away from this single interface, this transition radiation. We make an elementary particle, so to say, in nanophotonics, a small metal nanoparticle. This could also be a dielectric nanoparticle. Let's assume it's gold. Gold is full of free electrons. So what happens? The electron comes here, the negative charge, and it pulls and pushes on the free electrons in the gold here. That means they start to oscillate. They start to oscillate at an eigenfrequency that is determined by the property of the particle. Plasmon resonance, so electrons are displaced. There's a restoring force that is just determined by the density of electrons inside the particle and also the shape of the particle. So what's happening? The electron generates this oscillation in the particle, and that creates a near field, an electric near field around the particle. So the color bar here is the Z component of the electric field. It's induced by the electron and you see it oscillates. And this is the dipole moment inside starts oscillating. So T is pointing up, and half an optical cycle down is pointing down again, so it's oscillating different directions. Now the electron that actually induces this field, that field acts back on the electron. And that means the electron feels an accelerating and a decelerating force as it propagates through the near field, that it excites itself. And so the probability that the electron actually loses energy to the excitation is an integral over the accelerating and decelerating forces as it passes by. Electrodynamics is very simple, but no magic. This can be analytically calculated. And so, as the electron excites this, it loses energy. So if you do an energy measurement in an electron energy detector, you will see a shift, that there's some energy loss. So you get characteristic loss peaks that measure the resonances in that particle. So that's called electron energy loss spectroscopy, EELS. Every T in a microscope has an EELS detector. And then this plasmon, as it starts oscillating, these near fields, they will radiate to the far field and creates light emission. So if I put a photon detector here, I get my cathodoluminescence. But these are the two loss processes in electron energy electron matter interaction. So let's look again over time. What happens? The electron here, it was propagating, it moves an accelerating and a decelerating and accelerating force. So as a function of time, if you're the electron, this is what you feel. You get pushed on, you get pulled on, you get pushed on, you get pulled on. And now you have to do the net integral for this. You can see this is asymmetric. So there's a net result of this integral. That's the energy loss. So if you want to calculate the strength of that interaction, basically it's very simple. You need to integrate the electric field in the z direction. That creates work that acts on the electron. That's easy as a function of time. With this oscillation with the characteristic frequency, optical frequency in there. If you work this out, frequency is related to the velocity of the electron. We can define a wave vector. We know how time relates to position because we know the electron velocity. Forget about the details. You'll believe if you can write this, actually you can write this as a Fourier transform. But the axon actually couples specifically to specific spatial frequencies that match with the velocity of the electron. And simply said, it means that the best energy coupling occurs when the electron gets a kick all the time that is in phase with this oscillation of the electric field. If it's out of phase, it's accelerated, it's decelerated. So we're taking measuring the Fourier transform. This effect is strongest when there is Fourier components in this distribution here that match with the electron velocity. So you can say, we have a characteristic velocity of the electron in S. And it's about the electron distribution. And if I go to lower energies, I can make an electron have an effect in 10, 15. It's very slow. So it couples with light with a very small spatial frequency. Great, that's the coupling. Now, if you're an observer here and you have this metal nanoparticle and you stand here and if you have an electron that passes by and you're the observer here with that particle, what do you feel? Well, first the field is zero, then it comes closer, the field increases, and then it decreases. So as a function of time, the electric field, in this case, it goes down and it goes up again. It depends whether you look at this component or that component of the electric field. So the other one just goes down, goes up, and goes down. But that's the electric field that you feel at the distance of the electron. So that's in the time domain. So now let's take the Fourier transform. This is what it effectively is in the energy domain. You see that oscillation goes so fast that it has Fourier components that create energies or relate to energies from 0 to 30 electrons. It means that the electron can couple to anything resonant in the material in this frequency range. This can be the optical frequency range, it can be the requiring parameter, it can be the extreme ultraviolet. The electron beam carries all these frequencies with it. So in a way, it's a broadband light source. You do optics or photonic experiments here with an electron beam that's kind of a white driving light source. Very broad spectrum. It's also an ultra fast light source because that ripple is just a few femtoseconds. It's also very small. Spot size is only 5 nanometers. So that made for us the ideal probe to do optical experiments. It's just like our laser. Difference is a laser, it's oscillating, it's a fixed frequency. This particle comes by, and the difference is this particle has mass, it has charge, it's a broad frequency spectrum. So I got rid of most of my lasers in my lab, and we do nearly all the experiments now in scanning electron microscopes. Just bought a new, well, you buy maybe a new laser in your lab, we just installed a new SCM just to expand our capabilities in optical experiments.
And what do you need next? Like, do you want to go to higher energies or higher intensities, or is the?
What do you need for what?
Well, you mentioned that you bought a new.
Okay, why should you buy a new one? Yeah, for example, I'll show you later that we want to make pulses with the electron, pulse the source.
Yeah.
So then you're going to play with the electron point itself, and then needs a new microscope. Yeah.
Question related to the force acting on the reactors. And what we have talked about is probably the longitudinal forces that act on the reactor. But if you're passed by something like this polarized, your electron point, it also get deflected.
Yes, totally. That's also true.
Which does that affect, let's say, yield in terms of
Yeah, good question. No, so actually, if you put a position and a sensitive detector down there, you will measure it. It doesn't create work in that direction, so you won't see any energy loss. That's a good point. An interesting probe also. So one example in our initial work of how this actually works, is coupling to matter, how you polarize matter with electron beams. This is photonic crystal. But this is a membrane of silicon nitrate. It's 200 nanometers thick. And so the electron beam comes in this way, and here's holes in the membrane, so it's a photonic crystal. But here the holes are missing, so to say. This is a cavity. It was made as an optical cavity. Now we scan the electron beam across the structure, and we measure the light that's coming out. And so here you see a map, the light emission at here 750 nanometer. As the electron beam is raster scanned, so these are like 200 by 300 pixels. Every pixel we take a spectrum, we put the intensity at 750. So this is the mode, that's the cavity mode, actually 750 nanometer, of which we map the mode distribution.
So in fact, is a kind of spatial excitation spectrum.
Yeah, so what we actually probe here is the local density of states of that cavity mode. And then in the Z direction, the fields in the Z direction. And you have to realize this is silicon nitride, so this is not a semiconductor that emits light. It's a dielectric, there's a low density, the electron beam couples to that, and when the silicon nitride is polarized by the electron, it radiates. And the radiation is proportional to the local density of states.
And if you then make a spatial plot of the loss spectrum, you
complementary structure. So here you see a standing waves. Basically, this is the light flushing back and forth in the cavity that you can now resolve because you have high spatial resolution. So the electron beam polarizes the dielectric, which then emits light. No semiconductor needed. Now let's see. Let's play a little bit of further games. Now we take a gold nanoparticle here, a 100 nanometer gold particle on the nitride membrane. We put the electron beam on. Here's your first cathodoluminescence spectrum. So we come in with 30 keV. We detect the light emission here. So this directly shows the side is oscillating in the metal. We radiate to the far field. You can wonder how efficient this process is. The electron beam, loses energy, but that's a probability. The probability was that integral that I just showed you, the Fourier transform. It's about 10 to the minus 3. So for every electron that comes in, 10 to the minus 3 photon per year. It seems small, but if we have a 1 nanoamp electron beam, you have 10 to the 10 electrons per second, 10 to the minus 3, 10 to the 6 or so photons per second. We can count them all. So it's actually a very efficient process in optical experiments. Now let's play a few tricks. Let's say if we have two plasmonic particles on top of each other and the same electron excites both. What happens? It will tell us something about the coherence of the excitation. So we tried to do that experiment. It's not easy to lift a plasmonic particle up. So actually in the focused ion beam, we grew a needle here of silicon dioxide, and we coated it with tungsten, and then we coated it with gold at the top. So here's our first gold nanoparticle. See the top view in the SEM here. This is the first plasmon we're going to excite. And then here's a gold substrate underneath. Now we're going to let the electron beam pass by. And I told you, we can collect spectrum with this parabolic mirror, but we also collect the angular dependence. So we also detect how light is coming out as a function of angle. And that's in this measurement. It's very complex. There's a lot of data in here. As we project the light coming out from the mirror, in one direction here, it reflects the angular distribution. In the other direction, we put a slit, it's the spectral distribution. So here we can see, as a function of wavelength, how light is emitted as a function of angle. So let me guide you through. If light comes up all the way up, it's 90 degrees. That's actually the dark band here. That's the hole in the parabolic mirror where the electron beam goes through. So we don't collect any light. If we go to the side here, that's 0 degrees. That's where light couples out. And you see, if we go to the side, we see this interference pattern. So what this is the interference between the plasmon radiation generated from the first one. And then also it has an image charge on the other side here. Basically, it's reflection from the gold that's also coming out. And that creates this interference pattern. So we have these two sources. Now in this case, a metal nanoparticle, and then this image charge that is interacting with each other. We can take the Fourier transforms of this. So then from the frequency or the wavelength domain, we go to the time domain. Okay, this is hard to see, but here are these yellow bands or purple bands, several of them, that are representing the different time domains that are playing a role in these experiments. So yeah, the plasmonic particle radiating, we have this transition radiating, we have the image charge radiating, and altogether they create this interferometry. So yes, we have multiple interfering sources that are all coherently excited by the same electron. So the single electron has a probability to excite one plasmon, the other plasmon. They both have small probabilities, but they add up, they interfere coherently in the far field to create this radiation. And the phase difference between the two is then also determined by the velocity of the electron and, of course, the spacing. So then we said, okay, we're interested in these coherences. What happens if we have a substrate and we come in with an electron beam and we excite plasmonic or radiation effects at a certain distance in the lateral dimension? We then coherently add up all the radiation sources that come in from that single electron that comes down. So we come with an electron, we defocus it, so we irradiate a single area here from micrometer wide with a single electron. Probability spread out. We want to see if within that micron area, all the radiation that we excite is coherently adding up to one radiation profile. So this is a fundamental question. Either the electron collapses at a particular point and you just have a point dipole that radiates out, or if the electron coherently excites this entire area, you have to have a superposition of all these dipoles that all have a phase relation and radiate the particle. It gives a different radiation profile. So we can calculate that profile. So these are two models that we're testing now. If a broadband electron beam comes in and it collapses at one particular point, it will just have this angular lobes. This is an angular distribution in K space. So this is 90 degrees sideways. This is a radiation from a single dipole. But if we add up coherently all the dipoles that we could create in this central circle here, then we get this interference that creates an entirely different angular distribution. So now we defocus the beam and we try to test which of these two models do we get. And so here's the experiment. Data for very small spot or very large spot are very similar, and they all correspond to the single dipole that is radiating. So we can make the electron beam very wide, but the electron is not coherent over that very large area. That's why you don't get this coherent superposition for a large area. There's a probability for the electron to come at a certain position, and it collapses at a particular position and it creates radiation from that position. And so what does coherence here mean? The electron, of course, comes from a source, and it projects onto your sample. Electrons are waves. The de Broglie wavelength is 7 picometers. And so if the coherence of the electron beam, so that's how smooth basically the electron wave function is, it's a sample, is within that 7 nanometers. That means it's coherent. Means that all the effects that you excite should be coherently added up. And it's maybe not surprising in hindsight, but our SEM doesn't have such a good coherence that we can do over a large scale. So yeah, it collapses at a particular position because the coherence length is small. We're now doing experiments vice versa to find out, can we measure the coherence length, lateral coherence length of the electron? Yeah, of course.
So how do you distinguish between whether excitation is coherent or the radiation plasmon that is excited?
So I would say here in the two-particle plasmon, there, let me ask for this, there each excitation is coherent with the electron. Since the same electron excites these two particles, the radiation is also very coherent somehow, but they come in the same way. Now, in the lateral case, should I ask you a question? So you asked if the coherence, that the radiation is coherent, so that is yes in both cases. But the electron beam is not coherent in some cases. So make it too broad.
I could see a situation where the electron first coherently excites plasmons initially, but then before the plasmons get a chance to radiate, if you can see this plasmon as excitation profile.
Right.
So anti-phase,
And they dephase, yeah.
and it's not in the electron excitation, it's more in the radiation.
Yeah, but I think the message here is, the coherence length of the electron is so small that you cannot do it over such a large. Then the plasmon dephase, as you can have a plasmon polarities, for example, next thing.
So it's fair to say that what happens is that even though the beams see signs of the focused, the electrons are still formed particles.
Yeah,
essentially.
exactly.
Yeah, going down in various places. It's not that they broaden out, so they follow the component.
So where this is useful for, we think this is a new way of tomography that you can do. Let's assume you have a three-dimensional object and we want to know its dimensions and what shapes and frequencies. So now you can come in with the electron beam, and this is a model system that we focused ion beam milled into a gold surface. We put the electron beam in and we can generate this transition radiation that comes out. We can make plasmons. These are waves that propagate over the surface that can couple out. We can also excite this tip here. So there are many interfering sources coming out that all of which interference is a very sensitive measure for the shape of that dome. And so I have a few examples here of measurements that we did on these cubic holes. And this is just at the beginning. We're just starting the modeling of this. But this is, again, a square hole made in single crystal gold. And we put the electron beam in the center or near the slope or near a wall. And you see in the far field all these interferences building up, each of which are due to the interferences of all these different effects in the material. And right now, I give another example. Here we have a box. We vary the depth of the box, 0.9, 1.8, 2.7 micron. And you see all these different oscillations as a function of, this is the angular maps of the radiation. We can also model that. So you see, fine oscillations, sometimes represented in the measurements, broader field profiles. These are all the dimensions in the sample. And this is of interest. We do this together with ASML because they have silicon wafers that have geometries underneath the surface. These are maybe MOS type transistors, metal there, there's a silicon section, there's an oxide. And now we think if we come with the electron beam, that the radiation from all these different sources, some is coherent, some is not, in the far field, together, that whole package of data enables us to reconstruct three-dimensional damage. That's the idea. Demonstrate what the limits are. We think this is interesting because electron comes in, there is electron energy, we have the angular profile, we have the polarization dependence, we have the spectrum. We do the photon statistics, the T2 measurements, we also do these net package together. The question is how precise can you reconstruct your 3D material. So then, at the last part of the talk, I want to talk about an energy matter, electron energy matter interaction, where you want to have energy loss, but energy gain. So far, we talked about energy loss, where electron excites some resonance here, so you have an energy loss in your fields measurement. and part of the radiation comes out, and you have a CL cathodoluminescence spectrum. So how would we be able to get gain? Well, you have to add energy to this system. So you pump the particle with a laser while the electron comes by. Now we do an experiment where we have a nanoparticle. We come in with a very intense laser pulse that creates a very strong electric field around the particle, much stronger than when the electron is exposed to the particle. Tune that strength just by the laser power. And now we let the electron beam go through. And turns out what can happen as the electron beam passes by, it can pick up photons. The 10 keV electron picks up the 2 eV or so, then the laser frequency photon. So it actually gains. This is an effect first discovered by Zewel in 2009, and there was later theory and also further experiment by Klaus Ropers in Göttingen, who's really the hero in this photon-induced light scattering technique, who showed it was a quantum mechanical effect. And what I mean with that is this is a schematic, how this works. So here is your nanostructure, the electron beam passes by, and we come in with a laser, very powerful laser, to create a very strong light field. As we create that field, the electron comes through. That sounds simple, but it actually means you have to think about timing. You zap the laser, 500 femtoseconds. You have to come in with a pulsed electron beam too, to overlap them in space and time. I'll show you in a moment how we do this. So the electron that is first a fixed energy spectrum, maybe here it is 10 keV with some energy width determined by the source. Now it can pick up photons from this near field here, and its energy spectrum broadens. See it here. So here was the 10 keV, but now the electron actually picks up one photon energy, or 2, or 3, or it can lose 1, or 2, or 3. And this is a quantum mechanical effect where you have to look at this energy ladder here. So the electron is here. It can pick up a photon, can pick up a second photon if the power is enough, actually release a photon. So it actually is a random walk that is happening in this energy level diagram. We have to take into account all the phases, all the interactions, and that in the end creates this energy spectrum. This is quantum mechanics because the electron, as it passes through here, has this interaction, is in all these states at the same time. So the electron can pick up 1 photon or 2 or 3, you don't know, this is a probability distribution, till it clicks on the detector. If it clicks on the detector, it gives some count on one of the energy bands. But till it hits the detector, the electron wave packet is in this quantum superposition. Yes.
So does this phenomenon also happen if you just fire your electron through a vacuum and you close your laser, or do you need some kind of nanostructure?
Excellent point. So if you just cross the laser and electron beam, you cannot conserve momentum and energy at the same time. So you need this near field, this light field distribution at a small scale, because that provides spatial frequencies for those interactions. But just in free space, you cross the laser, and there's no way to match. That's why this only happens here. This sharp tip, we have a very small near field, very small, very high spatial.
The same thing is that the electron beam will not spontaneously radiate either. But that would be the reverse process.
Sure.
Because you need something to pick up the momentum.
Exactly. So this is fascinating, but now the electron, which we always thought was a point charge, that we also know is the wave, some distribution in space and time, that distribution is now going to change. Because some part of the electron has a high energy, so this wave packet part of it is going to move fast. But the same electron actually has also aspects that have a much lower energy, but can move slower. So the wave packet that was narrow in space and time is going to evolve over time. And that's why this fascinates us, because we wonder, it's interesting itself, tuned with the wave nature packet of the electron. Maybe you can use special spectroscopy. So I'm going to, at the end here, show you a few examples that we got started in these experiments. First with Klaus Ropers' lab in Göttingen, who has a EELS detector to do these measurements in a transmission electron microscope. And here we took plasmonic nanostars. These are colloidal nanostars with extremely small tips, 3 nanometers in radius. We pump this with the laser, we come with the electron, and we take the energy spectrum. And so here you see there's the 0 peak here, that's the 200 keV electron energy. And if we pump it hard enough, the 0 peak here completely disappears, and the electron either picked up 1 photon, or 2, or 3, or released them. And that's when the electron was positioned very close to this nanoparticle where the light field is very strong. If we move the electron beam a little bit further away here, this effect is much stronger. So, sorry, much less strong. So most of the electrons are still in the original state, but there's one sideband here. So the strength of this effect is determined by exactly the same integral I showed you at the beginning. There's an electric field, the electron beam goes through, it probes that field, and you have to take this integral over the trajectory. You can then go from this interaction strength to this ladder, so to do a sort of statistical analysis of how does this electron jump in all these different energy levels. And it turns out the distribution over all these states is given very elegantly mathematically by a Bessel function of this interaction strength. So there's a fixed relation between the amplitudes of each of these peaks given by this Bessel function here, where the energy coupling strength is determined by the laser electric field. Yes?
Is there a good argument why the zero peak vanishes?
Yeah.
Because it feels like a symmetry argument, but on the other hand, it should depend on distance.
So it's because there's also a phase involved in all this, basically Rabi oscillation, right? The electron goes into an energy state or picks up a photon state. So all these interactions have a phase in time. If you add it all up, actually turns out you get sidebands on one side and on the other you can state.
It's a random walk, and you can never go back to the zero.
Exactly. Yeah. So how do you do this? And this is now how we build this in our scanning electron microscope. You need to make pulses of both the laser and of the electron. So laser pulses we know how to make. We buy a laser and we give a 520-second pulse duration. 1 micron. How do you make a 500 picosecond electron pulse? Well, when you take your SEM, normally an SEM gives a continuous electron beam from the source. That's because you heat at the source and you pull out electrons with an electric field. So what you do, you switch off the heating, you switch off the electric field, and then you zap it with a laser. You zap the electron gun in your laser, in your SEM, with the laser pulse, and then by photo emission, electrons come out. Actually, a single laser pulse can create 1,000 electrons. So you can actually tune the number of electrons per pulse. You can easily make 1 electron per pulse, on average, of course, but you can go up to 1,000. So now we have an opportunity to design, of course, the electron pulse and the laser pulse, because they come from the same origin. So we just need to match the optical path to the laser that drives the source, the laser that goes to the sample, the electron that comes by, overlap them in space and time. Tell you that it sounds simple, but to find it the first time, you have to very good. Because we have to match this on a femtosecond time scale, or say a picosecond time scale. So we're talking about micrometers of dimensions here, over a path of several meters. Yes.
And using your electron gun in like a normal fashion for an SEM, that just randomly ejects electrons. You don't control over the exact moment that you.
No. So within the 500 femtoseconds, there is a relatively random process.
But I can imagine if you fire an electron with it by taking it through the light, those you also get some kind of distribution of points.
Yes, so you get a distribution over time as it comes from the source. And in fact, what happens then, if you have several hundred electrons in the pulse, you get Coulomb interaction between the electrons, which actually stretches the pulse. So that changes time distribution. So this is what we built. It's called a photo emission microscope, where a 250 or 500 femtosecond laser hits the tip, and then we vary the time delay to also hit the sample. We also have a microscope with an electrostatic beam blanker. So there you don't need a laser to hit the tip, but there you have electrostatic plates that sweep the beam and aperture. You can also make very short pulses. So I'll show you here, and I guess I'm coming to the end here, measurements that we did this way. So let's see, this part I have shown. Here's the first energy measurements that we did in the SEM, and I should add, I mentioned to you these fields detectors, and there's loss detectors that nearly every TEM has one. They don't exist for SEMs, hardly. So nobody ever measures the energy pulse or gain spectrum in SEM. So we had to work on this ourselves, and this was together with Peter Kruid in Delft, who built an energy filter, so retarding field analyzer. The way this works is the electron comes in with 10 keV. There's 10 kilovolt here, and so if the electron gains energy, it actually goes through If it loses energy, it's actually repelled back up. And then we change that voltage here over time, and in that way, we measure basically the transmission spectrum as a function of energy. We get the energy spectrum. So here's our first energy gain and loss spectrum taken in the SEM. For us, it was very exciting. We got this to work. We completely rebuilt the microscope. So this is the sample chamber, where normally here's your sample holder where you put your stuff and your samples, and many of you work with this. We've completely taken the whole thing apart to make basically an optical table inside, and sample alignment, and laser optics, all in the electron microscope. And this is the first energy gain and energy loss. We see the small side bands here in the initial experiment. So what's the initial experiment? We had a sample made by collaborators in Erlangen. This is a sample that's an array of silicon discs, basically silicon pillars. You can see better here, silicon pillars that we zap with the laser from this side. So now we have a strong electric field inside here, and then the electron beam comes in. So a strong laser pulse creates, zaps a pulse field here, same time comes electric pulse, and then they interact. And that creates this energy spectrum. And in that way, we can actually make a map of, as the electron beam goes through here, we can make in this two-dimensional area here, we can map at different positions the number of gain electrons that are filter the number of electrons that are not picking up photons. We only look at the transmission of electrons that picked up energy, and that is then a measure of the optical near. This is just the beginning, but this is our first near field map taken with this effect in the scanning electron microscope. Of course, refining that, trying to find the spatial resolution, and do this on complex structures. That's one final thing we can do with this timing experiment between light and electrons. If you make electron pulses, how do you measure how long the electron pulse is? You zap the tip, that's Coulomb repulsion. So what in reality is the length of that electron pulse? You don't have electron detectors with a picosecond time resolution. So what you do is you vary the time delay between the electron and the laser that generates this effect. And then you measure this quantum mechanical interaction as a function of the delay between the two. If they overlap in time, then you have this strong interaction. If they don't overlap in time, then this gain effect goes away. So we plot here the number of electrons that have gain as a function of the delay, and only when they overlap in space and time, we get these gain electrons. The width of the speed tells us then what the electron pulse ratio is. We could put the laser pulse ratio that we need. So we can also now do ultrafast electron spectroscopy because we have a time resolution that is coming from this effect. So the last thing I want to show you, I told you we're playing with this quantum mechanical wavepacket of the electron. The electron is in all these states at the same time. So some part of the electron goes faster, another part goes slower. So we're now doing simulations, and the next, of course, is experiments, is to see what can we do to control that energy spectrum and what does it mean for the shape of the wavepacket. And so here's a thought experiment first. We make a metal hole array. We let the electron beam go through, and each of these holes have a different intensity of light. That means each of these have a different coupling parameter in this energy spectrum. Then if we can coherently add up the electron waves that go through all these multiple holes, then we get a lot of control over the intensity of all of these cycles. So here are examples. If we make some particular distribution of light, we get 9 pixels, which, or here is a better example, different intensities. Some part of the electron goes through very intense laser field, another part of the electron a less intense laser field. Now we can calculate all these coupling parameters, we can coherently add it up, and we can create a particular energy loss spectrum. So for example, this is one we were aiming for. By optimizing this distribution, we can make an energy spectrum of the electron that looks like this. If we translate this to the time domain, if we let the electron propagate over time, because some parts are fast and some are slow, the electron that was first a blob in space is actually split in 2 parts. So this would work. We could cut an electron in 2 parts. First, statistics, the wave packet. Once you measure it, it clicks, and it's either in the front or the back of the tail. But till you do the measurement, it's in the superpositions. So now our question is, what's the spectroscopy that you could do? Can we entangle this state with some materials excitation that also has the same resonance times, for example, and do ultra-fast opposite spectroscopy? That could be both. So that's where the future is. And oh, this is the last thing I want to show. Here's again this meta surface, the electron beam going through, and I told you we can modulate the electron energy spectrum because normally we accelerate and decelerate the electron. We can also change the polarization of the light in the lateral direction. And that means electrons that are going through are either swept in one direction or the other, depending on the phase of the electron relative to the laser line. We now mechanically put a screen there. We could actually only filter out electrons that are at the extremes here. And that means you create a pulse train of attosecond electrons. Time. Here the question is, can we prove that? What can we do with it? These are all next steps. It says here transform back to light, because really what we're doing here, we use light to make electrons, and to make from the electrons spin light. You see, we use the electron properties and their quantum mechanics and their charge as a way to create new forms of light. With that, I'm at the end. So I showed you three concepts. Coherent excitation of plasmons with this interferometry interferomograms. Photon-induced near-field electron microscopy, that's the technical term for it. And then the idea that we can electron wave packet shaping using tailoring this effect. And finally, I'm going to acknowledge the many people that are collaborating in the group. PhD students and postdocs in my own group, collaboration with the Göttingen University, the Spanish groups that help us with theory and particle synthesis that provided some percents. That's it. Thank you.
Thank you very much for this inciting of the questions. Mike.
So I'm curious about the plasmon part. So you mentioned that to make like a needle part, to trap a plasmon there. Can you elaborate a bit on how this works?
Yeah. So it's not as ideal as I draw the cartoons, but so we basically have a needle, actually it's a silica needle coated with gold, and then part of it coated with tungsten, and tungsten damp is actually the plasmons. So what's left is a little blob of gold at the surface. Yeah, that's like 50 nanometer diameter, so it's a plasmon resin.
The idea is to get one, like the electron pass by, will excite of that plasmon resin. It's not those plasmons sitting there waiting to grab.
There was actually a question whether we would generate plasmons to propagate down the wire. Then it could also be here. And so that's why we coated with metal, but then the plasma.
Yeah, Fredrik.
I also have a question about this needle. So you started this part with the question, does the electron ever excite two plasma stations? I didn't really get what the answer to this question was.
Okay, so it has a probability of 10⁻³ to excite a plasmon. So it has 2 times that probability. But it's a single electron that does that. So you have to coherently add up the radiation from these 2 plasmons.
So which experimental result showed it?
They hit the appearance. In fact, there was a fixed phase direction.
Because I would expect that if the electron came from the side and only interacted with its thing, also the radiation. So once you decide the localized surface plasma the radiation also depends on the localized state. So it will create kind of an emission factor. The radiation efficiency will depend on where it sits. So you could still get.
I guess regards to the mirror, I would agree. But now we create the radiation in 2 positions. So the electron excites the plasma there, and it excites it also at the surface. So these are 2 sources of the radiation.
So you have to look at detail. It's not just with its image, but also
Yeah, you're totally right.
Is there a complication here with the case of 1 in 1,000? They'll use like 1 in 1,000, but that's a 1 in a million.
That's the point.
Like 2 statistically. So you need quite a lot of data to see this double excitation goal.
But the fact that it's a coherent excitation of the same electron is actually now the sum of the excitation.
But are you guaranteed that you excite both at the same time? And we could
Well,
excite one and not the other, and sometimes both.
yeah, and I think the experiment tools exactly that we excite two at the same time. We
Systematically.
see that indeed that's, the visibility of the interference fringes shows that it's 4 times the group.
Maybe something very naive. You show that you can tweak around quite nicely with these, so you can do lots of modifications to your scanning electron microscopes. Does that mean that you develop a microscope yourself? Because in my experience, it seems that a lot of companies like Thermo Fisher is, let's say, they're not very happy if you start modifying their equipment. So how does that work in practice?
Yeah, you lose the guarantee right away.
Yeah.
So they don't, as soon as you start playing with the source, they say you don't go to the life of the source.
Yeah.
So in fact, every year or so we apply it.
Yeah.
Which you know. Yeah, the sample chamber we really take apart, but that we have under control. But it's true. But we started with commercial microscope because there's still a lot of knowledge in the scientific problem. Although the more you open it up, the more you realize how simple it is. How much money you pay.
Yeah.
But,
Yeah, I was curious as to what your experiences with that was.
so I should say vice versa. This photo emission microscope we developed together with the they actually now sell it to customers based on our experience. Research contract with them. So you can actually now buy it for guarantee the laser coverage.
Yeah, thank you.
So, about future work, I guess that already, if you think about plasmons, and if you would try to think about applications in molecular optical spectroscopy, then now you have very powerful means for doing like time resolved Raman type of work. Because now you have an extended time and spatial resolution. So
Yeah, so these are the questions. I don't have a full answer yet, but can you learn about the phasing and plasmons and time scales for molecular excitations?
but also molecular excitation, because you can excite very intensely the Raman, then you also have due to this coherence, time resolution. It's probably so not only just applications, but also
No,
new
many
research
applications are
directions.
super far away actually.
Yeah. New research directions.
So you can see, for example, why they provide this time resolved system from Thermo Fisher. Because they make semiconductors for LEDs.
Yeah.
And they want to measure lifetime. Say the gallium arsenide, the gallium charge. It's very high spatial resolution. You see where the brain is.
Yeah.
So that's much less advanced than the spin effect, but you see it's a still on spectrum.
Yeah. Questions? If not, I'd like to thank you again.